Good morning, everybody, and thank you for joining us. So today we have the pleasure to have with us Professor Misko Cubrinovski and Dr. Ribu Dhakal from University of Canterbury, New Zealand. So the seminar will be divided in three sections. So Professor Cubrinovski is going to deliver the first and the last section, while Professor Ribu Dhakal is going to do the presentation in the middle. Before starting, I would like to introduce today's speakers. So Misko Cubrinovski is Professor of Geotechnical and Earthquake Engineering at University of Canterbury, Christchurch in New Zealand. His research focuses on problems associated with soil liquefaction, seismic response of earth structures, and soil structure interaction. Cubrinovski has authored and co-authored over 350 technical publications and has worked as an expert advisor on over 50 significant engineering projects. He had a leadership role in research efforts supporting the recovery following the 2010-2011 Christchurch earthquakes. His honors include the Ishihara Lecturer Award, the Ralph Beck Award, the Norman Medal, the University of Canterbury Research Medal, and New Zealand Geomechanics Lecturer Award. Cubrinovski is fellow of the University of Tokyo and is the immediate past chair of the Technical Committee 203 from the International Society of Soil Mechanics and Geotechnical Engineering. So good evening, Misko. Thank you for joining us. Dr. Ribu Dhakal graduated from the University of Canterbury with a Bachelor of Engineering with honors, finishing his undergraduate studies in 2017. He completed his Ph.D. at the University of Canterbury in 2022 with a research focus on liquefaction of reclaimed land using simplified and advanced analysis. He has authored several peer-reviewed technical articles and is now a postdoctoral research fellow studying the use of laboratory test data and advanced numerical modeling for liquefaction assessment of reclaiming soils and port infrastructure. His research interest is in geotechnical engineering, focusing on challenges relating to seismic design and assessment. So thank you, Ribu, for joining us. So I think I can just switch off myself. I will reappear at the end for the Q&A session.
Thank you, Anna, for the kind introduction, and good morning, everyone. So let me just share my slides. Right, so today, together with my colleague Ribu Dhakal, we are going to discuss some of the observations from recent earthquakes in New Zealand and our studies associated with those. And specifically, we will be discussing the liquefaction assessment methodologies for reclaimed land. As Anna pointed out, the presentation will have three parts. So I'm going to provide a brief introduction of case history, which is going to be really the basis for this talk, which is the liquefaction that occurred at the port of Wellington in a recent earthquake. So I'm going to introduce the type of damages that occurred, and we'll provide some details of the composition of the reclaimed soils, which are really at the center of this study. Then in the second part, Ribu is going to provide a lot of details around our studies to first explain the observations using simplified procedures, but then to identify key aspects in the assessment that engineers should really pay attention to. And then in the final part, I will try to provide some brief concluding remarks and allude to observations from other case histories and other earthquakes and the wider relevance of reclaimed land. So in the presentation, we will principally focus on simplified liquefaction analysis. We will briefly discuss advanced procedures, but most of the discussion will be around the issues related to simplified assessment. And in particular, we will address issues associated with complex fills, which are composition of materials that is different from clean sand, and that poses a problem and challenge in the liquefaction assessment. So one of the key outcomes or motivations of this study is to try to understand what are the implications of those kind of materials on the liquefaction assessment, and what would be some good approaches to address some of those challenges. So let me start with the introduction of the key case history that we will use for this presentation, and that is the Port of Wellington. And in the Kaikoura 2016 earthquake, widespread and severe liquefaction occurred at the port. So I'm going to introduce these key features of this event. So this is a map of New Zealand, and on the North Island here at the bottom is Wellington, the capital of New Zealand, which is a city with approximately 400,000 population. And in 2016, the magnitude 7.8 Kaikoura earthquake occurred. It occurred at this part of the South Island as magnitude 7.8. There were 22 faults participating in the rupture, and the surface rupture of the fault was over 200 kilometers. There were quite significant accelerations in this zone, but there are no major cities there. There are a few townships, and those were affected. And what we will be discussing today is really the effect on Wellington, which is roughly about 60 kilometers source to site distance from this earthquake. So now we are zooming on Wellington. This is part of the central Wellington, and what we are seeing here is really the port. So this red shaded area is the Port of Wellington. You can see a number of red symbols there. Those are strong motion stations where the ground motions were recorded, including at this location of the port. And this one here is another closest strong motion station to the Port of Wellington, which is called Centerport. And you can see here, this is the horizontal acceleration time history recorded at CPLB. You can observe peak ground acceleration is somewhere around 0.25 g, and we are seeing a reasonably long duration of strong shaking, exceeding 20 seconds or so, with a number of cycles. But the maximum amplitudes and the peak amplitudes are relatively moderate. So we would classify this as moderate shaking intensity in terms of amplitude, but it would be significant duration. Top right, you can see acceleration response spectra for 3 different classes of soils. You can see this black circle indicates location, which is on rock, essentially, on rock or nominally rock site. And the black solid line indicates the response spectrum for the ground motion observed there. Relatively low spectral accelerations with peak ground acceleration of about 0.08 g, so just 8% of the gravity acceleration. That would be a low acceleration on rock site. Once you go here, these are now strong motion stations on native soils, and you can see in native soils the ground motion was amplified, so it is approaching 0.2 g peak ground acceleration, and spectral accelerations were amplified across board, across all periods. And if you go in the reclaimed land here, including at the land of the center port of the Wellington port, you can see further amplification. So peak ground acceleration is 0.25 g, and significant spectral acceleration amplitudes across all periods, and especially large amplification in this domain from 1 to 2 seconds, which is due to site conditions, basin effects, and soft soil response. A combination of site factors contributed to this significant amplification. So the shaking intensity on reclaimed land was a bit higher and straddling between moderate and high intensity of shaking. And this shaking produced a significant liquefaction at the port. Before I go and describe the typical damages that we saw at the port, let me briefly introduce the land reclamation history at the port. This dashed line here is indicating the coastline in the 1850s, so almost 200 years ago. Since then, reclamation efforts started, and they were performed in 3 phases. In the early periods, some small-size reclamation works were performed, Then in the early 20th century, more significant reclamation was performed, and predominantly this gray shaded area was reclaimed in that period. In those frequently hydraulic placement was used, especially this large area was reclaimed by hydraulic placement, but also end tipping of gravelly materials in the sea was the alternative method used for smaller reclamation works. Then in the third phase, somewhere from 1965 to 1976, this part was reclaimed, which is now known as the Tordon reclamation. This is the thickest fill, and much of this discussion will focus on that particular fill. So the key is now that in Wellington, along the waterfront, there is a belt approximately 200 to 500 meters from the current revetment line, which is reclaimed land. And on these reclaimed soils, there is very significant infrastructure, and this is one of the most beautiful areas of the city as well. So clearly the performance of reclaimed land during earthquakes is extremely important for this city and for the Wellingtonians. So let's see what was the construction of the Tordon reclamation in particular. You can see an old image from the time of the construction. So approximately 3 million cubic meters of gravelly soils were dumped into the sea through truck operations. And the materials, local materials were used from quarries, nearby quarries, which were essentially gravel sand silt mixture. So the material was just dumped into the sea, and this kind of reclamation fill was constructed, as indicated here. On three sides of the reclamation, there is a sloping ground. Actually, there is no any retaining structure, 1.5 or 2 to 1. So modestly, gently sloping ground at three sides of the fill. And on the northern side is this confinement provided by an old retaining structure. So you can see that this Tordon reclamation, composed of gravelly soils, is quite thick, from approximately 10 to 22 meters thickness. It is essentially laterally unconfined except for the northern side. And it is not compacted because the soils were simply placed under the sea. When they surfaced above the seawater, they used rollers to compact the top 2 or 3 meters. So this orange layer is representing the surface soil, which was compacted, 2-3 meters of soil. And the yellow layer is the gravel sand silt mixture, which was not compacted. As Ribu will show later, probably in the details, whether the reclamation is mostly composed of gravel sand silt mixture, but also there are zones in which they use the relatively cleaner sands. So this blue area indicates such a sandy zone. And then the green layer is the marine sediment, the original native marine sediment layer on top of which the fills were constructed. And then the blue area is the zone of native alluvial soils, which are interbedded gravelly, silty and sandy layers that propagate towards deeper parts of the strata. So these are the essential characteristics, and we are going to focus mostly on the performance of the Tordon reclamation fill, and especially the performance of this gravel sand silt mixture. Due to the shaking that I introduced briefly, widespread liquefaction occurred at the port. Now we are seeing a part of the Tordon reclamation. You can see this southern tip collapsed during the Kaikoura earthquake. You can see also a lot of brownish color. This is pretty much ejected material. A close-up view is shown here, where the ejected material is really a mixture of larger particles, gravels, sand, and silt. And typically, the ejecta was occurring close to cracks or close to drainage pathways that provided an easy pathway for the ejecta to reach the ground surface. So you can see a pile of ejected material along the containers at the port. This is an aerial view of the Torden reclamation, schematically indicating how liquefaction was manifested. Blue painted area is area covered by water, brown painted area is area covered by gravelly ejecta, and light brown is area covered by sandy ejecta. So you can see that at a couple of locations, sand was the dominant ejecta material. And these are the areas where in the deeper part of the fills, there is prevalence of sandy soils, and that is why we are seeing the sandy ejecta there. So let's see now how liquefaction was related to the observed damages, and I'm going to use a very simple schematic here to indicate what happened there. So this is the pre-earthquake geometry. Due to elevation of excess pore water pressures, reduction in the effective stress in the fills caused by the liquefaction, there was significant loss of stiffness and strength, and as a consequence, large movements and displacements were seen. A key deformation pattern is indicated here, where you can see a settlement of the fill. Approximately in the center part was about 20 to 30 centimeters, and close to the edges it was half a meter or even more. This slumping due to liquefaction in the fills was also associated with a lateral movement, so lateral spreading occurred towards the sloping ground, and the lateral displacement pushed the wharfs which were supported on piles, so the wharfs displaced half a meter to a meter towards the sea. And you can see the offset created between the settled reclamation fill, indicated by yellow here, and the top of the wharf, which didn't settle much because it is supported on piles, was quite significant. So you can see here the interface. This is now the surface of the wharf, and this is the surface of the reclamation. Obviously, before the earthquake, that was a level ground. So quite significant damage was induced at the port. The port was out of operation for a while. The gantry cranes that you cannot see but are on top of this wharf were out of operation for 10 months. So as a critical facility servicing the capital of New Zealand, that was quite a significant impact due to the liquefaction induced in the reclamations of the port. What you are seeing here is the distribution of ground displacement due to lateral spreading. On the vertical axis is the magnitude of ground displacement in meters, and on the horizontal axis is the distance from the edge of the reclamation. So pretty much from this point, we are moving to the right, for example, about 200 meters. And you can see that the displacement at the edges were somewhere from half a meter to a meter. These are summary results from measurements at 4 different locations. And then you are seeing a gradual reduction of the horizontal displacement, permanent displacement due to spreading. So the spreading affected area approximately of 100 meters with very significant displacements, and then further up to 200 meters smaller displacements due to spreading were observed. And this is kind of typical. When liquefaction is associated with spreading, we are seeing damage typical for both, loss of stiffness and strength, affecting different foundations, producing a lot of settlement, and then lateral spreading is imposing very large unilateral displacements, which are obviously additionally damaging the land and structures. So these are some typical damages. Top left is a schematic view of the cross-section of one smaller building on shallow foundations, which was in spreading area. As indicated here, the spreading produced a stretch of the ground of approximately 30 centimeters, with pretty much ruptured extended the foundation at the foundation level and produced some structural damage as well. Top right is a view of the top of the piles of the Torden Wharf, where you can see substantial damage occurring at just beneath the deck at the top of the piles. And down to the right, you can see an area of a building, a part of a building supported on piles, this one to the right, and the reclamation area is, the original reclaimed fill is there. and you can see then an offset of approximately 0.4 meters. Obviously, before the earthquake, this was a level ground, so this was typical manifestation of large vertical offset between pile-supported area and reclamation that suffered a quite significant settlement due to liquefaction. So this is just a brief introduction of the type of damages that we were seeing at the port. So before I give the word to Ribu to continue, let me introduce some important aspects to consider in the assessment of the type soils that we encountered at Centerport. I will start with some general remarks about how we assess liquefaction in the profession using the simplified method. We use empirical relationships, and you can see such empirical relationships shown here by the black line. This is a CPT-based empirical relationship that allows us to estimate liquefaction resistance of soils if we know the cone tip resistance. If we perform a CPT, for any given depth, we can calculate this parameter, which is equivalent clean sand cone tip resistance. And if we know that one, so let's say it is 100, that we can go and at the intercept with the black line, we can read off the liquefaction resistance, which will be CRR, will be roughly 0.15. So for a layer with that QC1 NCS, we will estimate what will be the typical liquefaction resistance. And this is how we would use the relationship in simplified assessment. In essence, the cone tip resistance is a proxy for the density of soil. Low resistance is loose sand, moderate resistance is medium dense sand, and high resistance is very dense sand. So loose sand would show low liquefaction resistance, whereas very dense sand will show very high liquefaction resistance. So we can quantify the effect of density on the liquefaction resistance. Now, the key to emphasize here is that this relationship was largely developed based on evidence obtained from cases of liquefaction in clean sand. So most of the data that we have behind this relationship is from clean sand. We have to remember this very important feature. So what do we do in our assessment? So typically, this is the link that we use in the empirical procedure. So we have this relationship, which is in essence using CPT data. We use then the measured penetration resistance to correlate resistance to relative density. And then empirically, we establish a link between the relative density, between the QC and CRR. So the idea is through empirical relationships to establish relationship between QC and liquefaction resistance CRR. So if you measure QC in situ, you will be able to estimate CRR and then use that in your predictive tools when evaluating sites and effects of liquefaction in practice. Then, in addition to that, we add this link between the liquefaction resistance and relative density. So the next set of tests that we perform in the laboratory, we perform liquefaction tests for different relative density of soils, and in those tests we evaluate how many cycles are needed to liquefy the soil, and once the soil is liquefied, we evaluate shear strains and volumetric strains. So we can quantify the liquefaction resistance not only in terms of how many cycles are needed to cause liquefaction, but also what kind of shear and volumetric strains are going to develop. So the top part, the red part, are empirical relationships from field investigations and observations from case histories, and the bottom part, the green link, are empirical relationships from laboratory tests. We combine the two, and that is how we use to evaluate liquefaction resistance of clean sands, as well as to evaluate shear strains, displacement, settlement in liquefiable the soils composed of clean sand. If the soil is different than clean sand, so we need to do some adjustments. At the moment, practical procedures allow you to do adjustments if there is fines in the sand. So if there is some silt particles or finer particles than sand, not necessarily silt, could be even some clays, then we correct the measured penetration resistance is this one, and then we introduce correction factor because the soil that we are using to evaluate the resistance is not clean sand. If the soil would be clean sand, this term is 0. If the sand would include some fines content, then we have a correction factor delta QC1N. And once we do that correction, then the calculated QC1 NCS is used, and we refer to this procedure for clean sand. So in essence, there is a procedure for clean sand, which is used as a basis, and then there is a relatively simple way to correct the penetration resistance for soils that contain fines content, and that is what we use in practice. If I demonstrate or illustrate what that correction delta QC1N actually means in terms of the empirical relationship that I introduced before, in essence, there are several empirical relationships. So the black line is for clean sand, the dashed line is sand with 15% fines, and the red dashed line is for sand with 35% fines. So the correction delta QC1N is in essence a correction so that the red line is shifted and overlaps with the black line, and you will have smaller correction to shift the blue line to overlap with the black line. So in essence, this correction or delta QC1N is a function of the fines content. And that is what we do in practice. So in practice, we use fines content to simply correct the empirical relationship and have some simple way of calculating liquefaction resistance for sand with fines as well. Okay, that's great. So we do have some methods that deal with clean sands and sands with fines, but now the soil that we've got at this particular reclamation is gravel, sand, silt mixture. So definitely it is not covered by the types of soils that were used to develop or prevalent in the development of those procedures. As you can see here, the solid lines are all grain size curves from the ejecta samples obtained from Tordon reclamation, and the orange colored area in the background are the range of grain size curves obtained from these soils during the construction, indicating that this reclamation fill is predominantly composed of gravel. 45 to 75% is gravel, and the remaining 25 to 55 is sand and silt. Now remember, the way we calculate grain size distribution curve is by weight. So this is a percent finer by weight. So based on our traditional methods, the fill is mostly comprised of gravelly soils, which is obviously very different from the reference materials that were used for the development of this procedure. So this is one issue. How are we going to deal with this difference in materials? As I mentioned before, we have some established procedure for clean sands and sands with fines. And if we are dealing with gravel sand silt mixture, then we should be expecting several important effects of this material. The first one is on the packing of soil. So what will be the role of the gravel in the sand silt mixture? Which fraction is going to dominate the material? Is it going to be the gravel? So are we going to see liquefaction resistance typical for gravelly soils, or is it going to be the sand silt mixture? That is a very important question. As you will see, we will be focused on that one. The second is, once you have large and smaller and even smaller particles mixed together, they all show different penetration resistance, because we do know that grain size is affecting penetration resistance. So the next question that we have to consider is how this composition of soil is going to affect penetration resistance. And that is quite an important question, because we do use penetration resistance to estimate density of soil. Since liquefaction resistance is directly linked to the density, clearly any change in penetration resistance or change of density will implicitly imply effect on liquefaction resistance. So in our studies, we try to address these following questions, and Ribu will shortly provide many details around those. First question was, what is the controlling fraction in the soil matrix? Is it the gravel or is it the sand silt mixture? The second was the effects of the soil composition on the penetration resistance, and what will be the consequent effect on the estimate of the in situ state of soil, or what will be the effect on the estimated relative density of soil. And finally, we were trying to address this kind of questions and to see what kind of effects considerations of those or lack of considerations are going to have on the computed liquefaction resistance when we use simplified procedures. So with this, I will now shift to Ribu. Ribu, please take over for your part of the presentation.
Okay. Yeah. Thank you very much, Misko. Just checking that my mic is working. Great. Thank you so much. Yeah. Thank you so very much, Anna, for the introduction, and Misko for leading us on. So I'll continue as part 2 of our talk on liquefaction assessment methodologies for reclaimed land. And in particular, I do want to focus on some of the characterization issues that Misko has highlighted. So looking at perhaps more details in the soil composition, and then some of the in situ testing that we have done at Centerport in relation to some of those key considerations. We'll look at performance of existing simplified methods, and highlight some of those key considerations that one might have to account for in general engineering practice when applying them to those types of gravelly mixtures before looking at perhaps some more advanced methods, looking at numerical modeling and lab testing to supplement our understanding. Then I'll conclude and hand it back to Misko. So as Misko pointed out, the Centerport's quite interesting. There's two key types of reclamation areas that we're studying. So the top one is giving you an image of the gravelly reclamation. On the left is a historical photograph of when the reclamations were being constructed, and this is kind of what it looks like today. You can see the southern end of the port there, where Misko was showing some of the damage. And then on the bottom left, you can see some of the hydraulic fill areas, and this is what it looks like today. Quite a lot of urban development. So again, highlighting the importance of these areas and studying the ground properties. On the left here is a damage map, and I'm going to use this as a basis to start our discussion. This is a map of the liquefaction manifestation severity observed after the Kaikoura earthquake. So this is collating all that information with aerial photographs, ground photographs, drone image, LiDAR, aerial surveys that Misko was showing, and summarizing the damage that we observed on the ground surface. The different colors indicate the different severity of damage. So red being severe damage, and then yellow is moderate, green is minor, and gray is none. And then there's this purple region where there was severe lateral spreading type effects as well. We can see here the Thorndon reclamation, which is characterized by these gravel sand silt mixtures, largely had poor performances. And Misko suggested some of the key features that might have contributed to that. So the fills are thick. The edges of these reclamations are unconfined, which perhaps led to some of the lateral spreading, and then the deposition was largely in a loose state with uncompacted fills. And of course, we have this other area as well, which is the hydraulic fills. These are a whole different set of issues. We'll touch on them at the end, but this relates to issues around fines content, and plasticity. And you can see here it's also of interest to us because we saw varying manifestation performances. So the area of hydraulic fills, you can see some colored in red, some in orange, some in green, and some are gray. So we saw quite large variation of performance. So it gives us kind of a nice case study to also understand perhaps what the roles of the fines and plasticities and the profile characteristics were in its performance. So let's take a look at some of the characterization. Here I'm plotting again. This is the third time I'm showing it, but again, these black lines are showing those grain size compositions. And I just wanted to show as well the case studies from a couple of other well-studied case histories. So one is in Port Manta from 2016, and one is Kobe Port Island from the mid 1990s, where all three case histories saw liquefaction occur in port gravelly fills. And as Misko pointed out, some of the key features that encompass these types of case histories is that they are 40 to 80% gravel by weight. However, lab studies have shown that this is quite important to recognize that when you have a well-graded mixture or mixtures that have varying grain sizes, that actually when you the finer fractions can control the matrix if they are composed of at least 25 to 30% in weight. In other words, despite it being largely gravelly in terms of its composition, there's sufficient fines and sands to control the mechanical response of these fills, and we'll show that manifesting in some of the CPT data as well. So with that in mind, we went ahead and in 2017 to 2021 or so, we performed over 100 CPTs throughout the port. So on the left here, I'm showing a map view of Centerport. The blue shaded region is showing the Thorndon reclamation where the gravelly fills are. And these red dots are showing individual CPTs that were performed in the fills. These were performed using standard 10 square centimeter and slightly larger 15 square centimeter cone heads. And then these yellow pins are showing where borehole samples, boreholes were done with sampling of soils taken back to our laboratory as well. And so these sets of CPTs actually give us quite a lot of data to characterize these fills. And so on the right here, I'm plotting a summary of what that data looks like. So from around 75 CPTs performed in the Thorndon reclamation, I'm plotting here profiles. So as a function of depth, the cone tip resistance. This is data that is directly measured from the cone when performing the test, essentially measuring the resistance the soil exerts on the cone when it's pushed into the ground. The gray region is showing a range of values over the 75 CPTs as 25th and 75th percentile values, and then the black line is showing one CPT as an example of what the data looks like. On the right, I'm showing again a profile, but this time of I sub C. This is a geotechnical parameter that you can calculate from the CPT, and it's essentially the soil behavior type index. It gives you an indication of what type of material the soil is behaving like. And in this case, we're seeing again the gray shaded region showing 25th to 75th percentile, and then the black line showing one data. And by and large, what we can see is that these fills are characterized by QC of around 6.5 to 8 megapascals and I sub C values of around 1.9 to 2.3. These are actually values that are typically observed in silty sand sites or silty sand deposits, illustrating that actually these fills are reflecting the fact that these finer sand and silt fractions are controlling the mechanical response of the fills. In other words, the gravels are playing a quite passive role, and these values are reflecting the governing response of the sands and silts. You can see the role of the gravels do manifest in some cases, especially in these spikes here. So these spikes will be reflecting pockets of localized gravels or lenses of localized gravels, which the cone will interact with, causing these isolated spikes. But you can see these are only seldom occurred, and by and large, actually majority of the fill is characterized by these lower QC values. This data also allowed us to develop these cross sections, and so this was the cross section Misko was suggesting earlier, where we were seeing, a 20-meter thick uncompacted fill on the southern end, tapering down to about 10 meters of fill on the northern end as well, with this mound of clean sandy fill, which had slightly different CPT characteristics. But we can see here that our CPT data is reflecting the fact that these are essentially sand and silt controlled matrix, and perhaps indicates why we saw the performance that we saw during the Kaikoura earthquake. With that in mind, let's take a look at some results of simplified liquefaction analysis. So this is a summary of the triggering analysis that was performed for the sites in Centerport. So I'm showing again the liquefaction triggering procedure that Misko showed earlier. So on the x-axis, we're showing QC1NCS, that CPT parameter, and then this line is indicating the liquefaction resistance estimated using these empirical methods. Two things to observe. The first thing is that these dots, which are the critical layers of the CPT profiles, and in particular the green dots, which are the Thorndon reclamation, have QC1NCS ranging from around 50 to 100 or maybe 45 to 90. And that range of QC1 NCS is really in that loose to medium dense range here. So we're definitely seeing the effects in terms of the uncompacted nature of the fills manifesting as low QC1 NCS values. And then the second thing we'll observe is that the data points lie in this cloud shown in the red shaded region, which is all above this black line here, suggesting that in fact these triggering methods are estimating liquefaction to occur with factor of safety in the range of 0.4 to 0.7. So it's suggesting that these empirical methods are actually correctly estimating liquefaction to trigger for this earthquake, for the Kaikoura earthquake in 2016. Having a look at some settlement estimates, we can start getting some further insights. Here I'm showing comparison at 16 different locations where CPTs were performed. So these are 16 different CPTs that were performed within 5 meters of aerial surveys used to estimate the settlements. And so these bars are sort of showing the estimates of settlement measured. Estimates based on the CPT-based analysis, which are these dark black line bars, and then the lighter bars or the blue-colored bars are showing what was measured using the aerial survey. These CPTs are ordered from those that are closest to the edge of the revetment. So in this case, it's 16 meters from the edge of the reclamation to, on the rightmost case, around 280 meters or 278 meters away from the edge of the revetment. So this is perhaps closer to the center of the reclamation. When we're studying this data, there's two key observations that one can make. Firstly, if we just focus on those that are on the right-hand side of the plot, we can see that by and large, in general, we're estimating slightly lower values than what was measured. So by and large, these darker bars tend to fall slightly below the blue bars, which is not surprising given the fact that there are perhaps different mechanisms of settlement that are not being captured by these estimations. And the second key observation is actually when we look at the sites that are closest to the edge of the revetment, you can see there's much larger underestimation. For example, if you look at the leftmost case, we're seeing that actually we're off by a factor of 2, estimating around 200 millimeters of settlement when in fact we observed around 400. And this is reflecting the fact that these sites are dominated by lateral spreading. Recall Misko showed the schematic at the bottom here, and he was showing that while you're having more free field type settlement down the middle with slumping mode of failure, you actually have additional settlements due to this lateral spreading effect, causing these kind of 2D and 3D deformation modes that are not being captured by these simplified analyses. And so this is perhaps reflecting the fact that these sites near the edge are not really free field sites per se. And so really the data is revealing what we had observed with our reconnaissance as well. And so with that in mind, while we say that yes, these triggering analyses are performing reasonably well, we can start isolating areas where it perhaps breaks down as well. One of the key issues that we looked at was state characterization, and in particular the effects of particle size on penetration resistance and the effects of the grain size distribution on the penetration resistance to relative density correlation. To dive into further details, let's look at some data that's available in the literature. On the left here are typical correlations that one might use in engineering practice, and these are 3 sets of curves shown with 3 different lines, all developed for using soils that are silty sands or clean sands. So these are more aligning with the case histories that were used to develop the triggering procedures, and you can see here that as QC1 increases, so in other words, as our penetration resistance increases, our estimate of relative density also increases, and all of these data pretty much fall in this band here, band of lines shown in the left. On the right side, I'm showing a set of curves from another study. This is from Cubrinovski and Ishihara, 2002 and 1999, where they developed curves using a wide range of soil types. So in this case, rather than just using sands, they also included silty sands, some silts, some gravels, and some gravelly sands. So now we're looking at using a wide range of soil compositions and seeing the effects of soil composition in its packing characteristics and therefore its penetration resistance and its correlation to relative density. What they found was this parameter Emax minus Emin, which is the maximum void ratio minus the minimum void ratio, or the difference in the 2 extreme void ratio cases in its densest and loosest packing, is a key material parameter that can actually describe the effects of particle size. on its penetration resistance. So for example, if we take typical Emax minus Emin values measured in the lab for clean sands, we can see that their curves actually fit around this band shown in the top set of shaded region. And what we can see is that when we use these typical values, actually these curves align pretty well with what the general engineering practice uses, particularly if you take a look at this red line. The red line is what's used in the well-known Zhang et al. Relationship for estimating settlement, for example. So this is the Tatsuoka 1990 curve. And so by and large, you can see that actually the traditional methods agree pretty well with this study here. However, we can see that if we adjust Emax minus Emin to values that are typical for clean gravels, we can see the effective particle size on the penetration resistance and its relationship with relative density. So if we use typical values for clean gravels, we can see that these curves sit much lower, and for gravel sand silt mixtures, it might be somewhere in between as well. So for example, if we were to measure a QC1 NCS of 100 in a clean sand deposit, that might actually reflect a relative density of around 65 to 70%, whereas for gravel sand silt mixtures, it might actually be reflecting a relative density of around 50%. And so you can see here that using traditional curves like the ones on the left might actually overestimate relative density. And so now we can start isolating the effective particle size on these relationships as well. And so the question is, what implications do they have in terms of the simplified procedures? Well, let's take a look at one example to illustrate some of the effects that one might see. So here I'm plotting one of the profiles, one of the 75 different profiles we have in the Thorndon reclamation, and I'm plotting profiles of QC. So this is the cone tip resistance again with depth, and we're seeing QC here, typical values of around 6.5 to 8, just as before, with those isolated spikes, and the fill ends at around 15.5 meters, and again I sub C values of around 1.9 to 2.3, just as before. The third profile is showing estimates of relative density using two different correlations. The red line is showing correlation, this red line here, so you're using this red line on the left, gives you these relative density estimates, and it's estimating relative densities of around maybe 55 to 70%, which is actually in the medium dense to slightly larger density estimates, whereas the gray zone here, which is accounting for the different grain size packing characteristics, with the range depending, reflecting the fact that we have uncertainty in our Emax and Emin values, suggesting that actually DR estimates or relative density estimates are around maybe 30 to 50%. And that has consequent effects in terms of the calculating settlements. So Misko suggested that these relative density estimates will therefore affect calculation of strains and therefore calculation of settlements. And we can see here that if we were to use the traditional sand-based methods, one would estimate settlements of maybe around 20 centimeters, whereas using one that captures the effective particle size on penetration resistance might actually reflect something around 40 to 50 centimeters, perhaps something closer to what was measured at the site. And so the key conclusion that I want to take away from this is that sand-based relationships can tend to underestimate settlement in gravelly mixtures, or I should say gravel sand silt mixtures, due to overestimation of relative density. And so really the state characterization and characterization of relative density is quite an important detail when looking at these types of problems, particularly given that we have quite large settlements, and in fact we were seeing some underestimation of settlements as well. So that's hopefully a quick overview of some of the simplified procedures. We're seeing if we can get some additional insights from advanced numerical modeling as well. So I'll spend a few slides on just covering some details from advanced modeling that we've been doing. So this is looking at 2D analysis of a pile-supported wharf on liquefiable gravelly reclamation. And in particular, we're trying to capture some of the effects that we saw on the reinforced concrete Thorndon wharf, and in particular looking at some of the lateral spreading damage that we observed after the earthquake. And so this blue box is kind of indicating the behavior that we're trying to capture in our analysis, and perhaps use that modeled for future analysis, future prediction as well. On the bottom here, we're showing an overview of the numerical model that we've been playing around with or analyzing, and these different colors are showing the different soil units based on our CPT-based characterization. So these are still being informed by the CPT data that we have collected. We can see the top blue layer here is the compacted gravelly crust, 3 meters thick, and this large green region here is the gravelly fill, and that's essentially our key liquefiable layer that we're modeling. in addition to the presence of the Thorndon wharf shown in red here. Note that this cyan or blue layer here is essentially our marine deposit. So this is our a soft marine deposit layer or beach deposit layers overlying these different interlayered alluvium soils. In terms of modeling, so one of the key considerations in modeling is actually modeling these liquefiable soil layers, and so we're using well-established empirical liquefaction resistance curves in terms of our modeling. So on the right-hand side, I'm showing a plot of cyclic resistance ratio. So this is our resistance to liquefaction as a function of the number of cycles. So these are what we call in geotechnical earthquake engineering typical liquefaction resistance curves that are used for our calibration. And these different lines show you the resistance for different QC1 NCS based on those empirical triggering charts of Boulanger and Idris. So for example here, if we take a look at just 15 cycles, which is somewhere around here, a high density soil will have a much larger liquefaction resistance than, say, a QC1 NCS of around 50, which will have a lower resistance, and that resistance is also a function of the number of cycles to liquefaction. And so in our numerical modeling, we calibrate our constitutive model parameters to capture these curves as closely as possible. We can see here a single element simulation performed on one case, which is giving us this triangle point shown by this arrow here, and we would repeat these for a range of cyclic load demands and a range of relative densities to capture these curves as closely as possible. So that's the first detail in terms of our numerical modeling is the liquefiable layers. In terms of our deeper non-liquefiable layers, it's important to capture the general shear strength and degradation of stiffness characteristics. And I'm sure some of us that have looked at earthquake engineering problems perhaps have done this in a total stress sense. But essentially, we're trying to capture the estimated strength and the degradation of stiffness using just even empirical estimates are sufficient in this case. So in this case here, we're looking at one layer. The black line is showing one of the target stress strain curves that we might want to capture, and then the red line is showing our numerical model that trying to capture that curve as closely as possible. So that's our calibration of our non-liquefiable layers. And then finally, we want to also calibrate our soft marine deposit. And so in this case, we're allowing for the model to actually develop some excess pore pressures. But you can see here that the vertical effective stress on the x-axis of this bottom right plot, while it does decrease as we load that element, it doesn't decrease to completely zero, which is typically what you observe in these finer, softer soils, also associated with further degradation of stiffness as you load it. So the final key consideration is input ground motion, and so we were looking at some of the strong motion stations, and Misko showed some of those spectra as well from a rock site, a site on native deposit, and a site on reclaimed land. And so we want to use these sites as potential input ground motions as a realistic input motion for our numerical model. And so the key here is to take some of these motions. So in this example, if we were to take, say, for example, the VUWS motion, deconvolve it to an equivalent bedrock motion, convert it to an equivalent outcrop motion and use it as an input in our numerical model, and then perform our site response analysis, which will then give us our results in terms of our analysis. So this type of approach will give us a realistic input ground motion, which will then be used to give us an output in terms of our analysis as well. So a key consideration as well as in our modeling is input ground motion selection as well. So these are just typical results, just to illustrate some of the additional insights one can gain. So on the left here, I'm showing results for a low seismic demand of PGA 0.2 Gs. And on the right here, I'm showing results for a high seismic demand of PGA 0.4 Gs. And on the top set of plots, I'm showing results in terms of pore pressure, excess pore pressure ratio, and on the bottom I'm showing crest displacement contours as well. And by and large, we can see that for the lower seismic demand, we're seeing that some of the fill is liquefying. You can see this blue region here closer to complete liquefaction, with associated crest displacements of around 1 meter, whereas if you have a higher seismic demand, we're seeing much larger crest displacements due to more liquefaction occurring as well. And so these are giving us insights in terms of the mechanisms. So we can see here liquefaction is causing this large kinematic demand on these piles, which is then therefore causing much of this movement that we observe, or much of the load that's being exerted onto the piles, giving us these large crest displacements as well. Here I'm just summarizing the results in terms of the lateral spreading on the surface. So here I'm plotting the horizontal displacement along the top surface as a function of different input PGAs as well. So before we were looking at results for PGA of 0.2 Gs, which is maybe close to what we observed in the Kaikoura earthquake, which was estimating lateral spreads of around 1 to 2 meters. Whereas larger earthquake demands might give you, larger lateral spread estimates near the crest as well. I'll go over this detail, but I just want to cover the last thing as well as some of the laboratory testing, giving us further insights as well in terms of the hydraulic fills. So until now, we've been looking at analysis of the Thorndon reclamation. So these are these gravel sand silt mixtures, but also of interest as well as the hydraulic fills here with issues regarding fines and plasticity. And so I'll just spend a couple of slides looking at some of the laboratory studies that we've been doing to gain insights in terms of its performance as well. By and large, a lot of the efforts have been looking at sampling of soils for testing back into the lab. So we go out onto the site with drill rigs. Contractors will then drill the soil out, extrude the soils. So we have either high, soils with high fines content or very soft soils, and some soils that are more sandy or shelly, and then transport them back into the lab. You can see here a lot of effort is placed into making sure that these samples have minimal disturbance. So we can see, for example, foams around the edges of the soil tubes, perhaps allowing for more damping of some of the energies that might be imparted during the transport process, so that when we're taking them into the lab, they have minimal disturbance. The ultimate goal is to then test them into these triaxial devices. And so we take these devices and try to test them. For the case of the finer soils, we will extrude them, trim them down, and then test them in the triaxial device. Whereas for the sandier soils, we will freeze them, core them, and then test them into the triaxial device as well, which will then cyclically load, as you can see in the video, and measure strains and deformations and responses in terms of pore pressures and changes in these stress states. So these are some of the testings that we've done. And just to give you some typical results that we see. So this is a typical result of one of the fine-grained samples. So here, for example, is a fine-grained specimen. This was where I sub C of around 3 was observed, and the plasticity index of around 36. We can see the vertical effective stress reducing with loading cycles, and just like we saw in some of the numerical modeling, we can see here that the effective stress does not drop all the way down to 0, which is typical for fine-grained soils. Whereas if we look at a result for a typical sandy fill, where I sub C was maybe around 2, we can see that the vertical effective stress drops all the way down to 0 with typical butterfly loops. So we can start seeing the effects of perhaps a high plastic soil versus a specimen that has no plasticity with lower fines content, and start characterizing the difference in terms of the behaviors as well. Just to finish my part, just to recap again, so liquefied gravels at Centerport, they had very important characteristics in that though they had 40 to 80% gravels content, they had 20 to 60% fines and sand content, and this is quite important as that's sufficient for the finer fraction to control the matrix behavior of the soil. We saw that CPT data illustrated the dominant influence of the finer sand silt matrix and illustrated the fact that these fractions tend to control the mechanical response of the fills. And the liquefaction assessment results are consistent with observations by and large for the Kaikoura earthquake, though we did highlight some of the limitations and some of the reasons those limitations are observed. We've highlighted characterization of relative density as a key issue in the CPT-based methods, and we also highlighted perhaps some of the issues in terms of traditional correlations of relative density with CPT penetration resistance, and some of the perhaps suggestions and alternative methods that one can use to what is traditionally done in practice to estimate relative density and its consequences on settlement. We then quickly touched on advanced methods to capture complex soil behavior and perhaps additional deformation mechanisms that simplified procedures cannot capture, and then gave you an introduction in some of the laboratory testing that we've been doing to give insights on the roles of fines and plasticity of hydraulic fills on its dynamic response as well. So a whole heap of issues that we're covering, but hopefully it gives you a quick insight into some of that work. I also add this here. I hope perhaps you'll be able to see the recording afterwards if you do want to revisit some of the details. Just bear in mind that these are the relevant readings. That if you want to visit any of these details that we've talked about, and some of the details Misko might continue talking about in terms of liquefaction effects from the Kaikoura earthquake, some of the CPT data, some of the liquefaction assessment we've been doing as well are in some of these readings if you are interested. So with that, I thank you for your time. I'll obviously stay behind for questions, and I'll hand it back to Misko to take us home.
Thanks, Ribu. So let me make some brief remarks at the end. I will repeat a few things that Ribu mentioned as a sort of concluding remarks. So one important issue was the composition of the soils that we had at Thorndon reclamation, which is a gravel sand silt mixture. And our key finding was that despite the predominance of gravel in terms of weight, 45 to 75% gravel, actually the soils were controlled by the sand silt matrix. So that's quite important. And then it is also important to emphasize that the gravels actually, you can see that most of the gravels are fine to medium gravel size particles. This is quite important. If you would have very coarse gravel, maybe the effects would be slightly different. So sand silt matrix plus fine to medium gravels actually explain why the material is behaving as we have observed in situ, in analysis, and in the laboratory. So why is the controlling matrix important? If you see at these two schematic plots, to the left, large particles are going to control the mechanical behavior. To the right, actually fine particles are going to control the mechanical behavior. For the grain size distributions that I was plotting, if you visualize what is happening in terms of particles, it looks like what I'm showing here. The small particles here are sand and silt, actually sand, and the gravel particle that you cannot see, there is one yellow circle, that is the gravel particle. So actually, gravel particles cannot be seen because there are too many small particles. So it's not really the weight of the particle itself, but it is the number of particles surrounding a given gravelly particle, which essentially results into this kind of matrix, and that is why the sand and silt control mechanical behavior. That means they control what will be the effective stress path, cyclic resistance, as well as how strains are going to develop, and that is why it is so important to estimate or identify what is the controlling matrix in this kind of complex mixtures. The second important issue that we brought to attention to is that now the particle sizes also affect the penetration resistance of soils. Ribu did mention that study that we performed some time ago, and this is the key relationship from that study. On the horizontal axis is the void ratio range, E maximum minus A minimum. Small values are for gravels, but these values here are for sands, and to the right are for sands with fines. And we can see that the penetration resistance ratio to relative density is very high, for gravelly soils, reduces for sands, and it becomes very low for sands with fines. So clearly, the particle size and the void ratio characteristics are affecting the penetration resistance. If you use now this empirical relationship, you will find that at a given relative density, say 60%, the SPT blow count is going to be very different for clean sand and sand with fines. So for clean sand, at 60% relative density, the SPT blow count is going to be 18, and with sand with 30% fines, it is going to be just 8, so less than half. So clearly, the composition of soils, and in particular particle size, is affecting penetration resistance. This is very important because then we use penetration resistance in our subsequent simplified analysis to estimate relative density and then estimate settlement. And Ribu showed that if you use empirical relationships for clean sand, the settlement estimates will be smaller than if you use empirical relationships that account for the complex mixture. So in that sense, the grain size composition affects the matrix, key behavior, and also affects the state of the soil in terms of density, which is a key input in our liquefaction assessment. So we need to modify the relative density of the soil to account for the complex composition and then apply the methods that are based on clean sand. By the way, we were doing those studies long time ago because of this particular case history that I want to relate to. So in 1995, there was an earthquake that affected Kobe, one of the larger cities in Japan. And it was a magnitude 7.2 earthquake. The source was very close to the city, and there was significant damage throughout the city. And liquefaction occurred, especially in this waterfront area. You can see the islands have very straight lines and regular shapes because they are all reclaimed land. So significant liquefaction occurred in some of these islands. I'm going to show you a few images from the Port Island because we have spent a lot of time and studies. I have performed studies for 10 years on this earthquake. So let me show you a few characteristics of the soils and damages at Port Island. So this is an aerial view of Port Island. You can see the dimensions like 4 kilometers by 3 kilometers. So it's quite a large island. The yellow painted area is actually area covered by ejected materials, and those were mostly gravelly soils, as we will see shortly, very similar to those at Wellington Port. There was a vertical array, so the ground motion was recorded at Port Island, so we have excellent records and a lot of great and well-documented case histories on the performance of different types of structures. So this is an aerial view at this corner of the island. So here is the vertical array, and you can see the whole island is really covered in yellow. It should be gray asphalt area, asphalt color, but the yellow indicates the ejected material, so it was all covered in soil. And this is how it looked immediately after the earthquake, completely flooded with a lot of ejected material beneath the water. And the high excess pore water pressures, because the fills are quite thick, about 20 meters thick, the generated excess pore pressures were very high, so you can see the severity of the pressures was causing eruption of soil and water up to 1 meter above the ground surface. There was massive settlement at the island. As you can see, this is now elevated railway, which is supported on piers, on piles. The piles go 40 meters deep, so that the structure didn't settle. But you can see that the whole street around that settled. So you can see this significant offset close to half a meter of large settlement of the whole area. This is high-rise building, over 20 meters tall, over 20 stories tall. On pile foundations again, so the surrounding fill settled and the building didn't settle, and again you can see those offsets. This is entrance to such building where the offset is about 70 centimeters, so huge settlement throughout the whole area, very similar to what we were observing at Center Port. At Port Island, the quay walls, there were massive quay walls, about 12 meters wide and 80 meters high, and the backfill is the reclaimed fill. They were replaced soil was the foundation soil. Unfortunately, they excavated the original clay soil and replaced it with sand. So liquefaction developed in the foundation soils and in the backfill, and consequently there was very large movement of the retaining structures of the caissons towards the sea. And this is a summary of those movements, horizontal displacements on the horizontal axis and vertical displacements on the vertical axis. The movements of the walls horizontal movements were roughly from 1 to 4 meters. So due to liquefaction in the backfills and in the foundation soils, there was instability and significant movements of the caisson, including this kind of deformation with sinking of the wall into the liquefied foundation sand. So quite substantial and severe effects on all sorts of structures. And the soils, well, as Ribu pointed out, the soils were very similar to what we observed at Centerport. So this gray shaded area are Centerport soils and all these lines, and orange shaded area are the soils at Port Island in Kobe. Clearly very similar composition. So everything we've said about the Centerport soils apply to Kobe Port Island soils. This is the penetration resistance in those fills. Unimproved fill is this one here. Very low SPT blow count, somewhere around 6, 7, 8, which is indicative, same what we were seeing at Centerport, very low penetration resistance, because the sand and silt are the controlling matrix, and this is really governing the penetration resistance, which in turn would show very low liquefaction resistance. So the red line here is the measured liquefaction resistance on in situ soils recovered from in situ in their preserved density state, because they were obtained by ground freezing. So clearly, low liquefaction resistance will be associated with those soils due to low density or low penetration resistance. So as a final comment, I just want to emphasize that the reclaimed land case history in Wellington is really very instructive for a lot of vulnerabilities associated with liquefaction hazard that we have with reclaimed land throughout the world. This is the particular timeline of the reclamation history in Wellington. These are the 3 phases. They were all happening long time ago. The last one was from the 1965 to 1975. And you might be well aware that the first significant event in which liquefaction was noticed as a significant engineering issue was in the 1964 Niigata earthquake. So our methods for liquefaction assessment evolved after 1980s. So in this last 40, 50 years or so, which is after the development of reclamations. And this is the story throughout the world. Much of the reclamations have been developed in relatively simple ways for construction using liquefiable materials without any densification, and they're obviously placed in an environment of high seismicity quite often, and that means their vulnerability to liquefaction hazard is extremely high. We just need to be aware that actually reclaimed land is one of the critical issues associated with liquefaction vulnerabilities. Those are constructed fills of liquefiable materials with very low relative density, meaning that once they liquefy, they're going to show very large deformations and going to produce quite significant damage to structures and facilities. So at the end, just a summary remarks around everything we have presented. Our simplified procedure are centered around clean sand, which was used as reference material in the development. So those procedures have greater uncertainty in evaluating liquefaction resistance of soils other than clean sand. We have to recognize that there is significant grain size effect on the penetration resistance, which in turn affects our estimates of relative densities. So we have to be careful how we apply those empirical procedures to different types of materials. It is also important to understand that the controlling fraction in the soil matrix is extremely important to evaluate the mechanical behavior of different soils. So we need to consider the composition of soils and see what is the most likely fraction in the complex mixture that is going to govern the behavior. The summary on the Torden fills, those were very thick, unconfined, loose gravel sand silt mixtures. They're relatively young and of weak fabric. These all point towards very low liquefaction resistance, which was manifested during the Kaikoura earthquake. We understand that the complex mix is actually controlled by the sand silt matrix, despite the large percentage of gravel, because with the number of particles, fine particles, they control the matrix, not the weight of the soils. And these findings are all consistent with the liquefaction observations, where we really saw very severe damage, which is typical for sandy soils. And finally, we found that if we apply conventional sand-based relationships, we are going to underestimate the relative density for those mixtures. So in summary, it is fine to use simplified liquefaction evaluation procedures for such materials, but it should be carefully applied to such soils, and we need to scrutinize every aspect of the procedure in which we anticipate that such soils are going to have profound effect either on the relationship or the interpretation of data. And if such interpretation is accounted for, then obviously it will be fine to apply simplified procedure to even more complex mixtures and soils, as was in this case of Wellington port. Well, thank you for your attention, and with this we are concluding the presentation. So Anna, it's up to you how you want to finish the session. Thank you.
Thank you, Misko. Thank you, Ribu, for this outstanding seminar. So we'll learn a lot today. So thank you so much. I already collected some questions from the students, and I encourage other students to do questions using the chat box. So just raise your hand. So, okay, so I have just one question for Dr. Dhakal. Do you think that the lateral spreading at the edge is the cause of the underestimation of the vertical settlement respected to the measured ones?
Yeah. So the lateral spreading is more pronounced in the edge. It's not to say that it didn't propagate inland, but lateral spreading is more pronounced in the edge, and that's associated with additional settlement, or let's say additional vertical movement as well. Whereas these simplified methods are really a 1D pseudostatic analysis, where you're just capturing settlement due to reconsolidation. So it's a different mechanism that it's capturing. If your site is dominated, is free field, and it's dominated by that mechanism, you'll get closer estimates. But in the case of near the reclamation edge, we had it was dominated by a different mechanism that these simplified methods cannot capture. And so that would be the reason behind why we were seeing those large underestimation. Yeah.
So thank you, Ribu. I have another question coming from another student, which is related to this in situ investigation. So I don't know who would like to reply. How difficult was to perform the CPT in this type of soil, considering that there is a huge amount of gravel?
Go ahead, Ribu.
Yeah, definitely not easy, I'll say. Look, when performing CPTs in these types of soils, it can be done, but you do need to pay attention to some of the details. So one of the details that we paid attention to, for example, was we used predominantly in the gravelly fields slightly larger cone size. So we used a slightly larger penetration cone diameter, which means that there's more likelihood of it actually penetrating through the ground through those lenses of gravels that we saw in some of the data. We also pre-drilled the top 3 meters. The top 3 meters of the fill was above the groundwater table, and that was the only compacted part of the fill. That couldn't be penetrated with CPTs, and so we pre-drilled, through that part, and then started from 3 meters depth. So that was another quite important care that we took. And we also, made on-site decisions. For example, I spent months there, and oftentimes we would penetrate to say 10 meters depth, we would hit refusal, and then we would drill a hole maybe 3 meters away or 2 meters away, down to 10 meters depth, and continue penetrating there. And so that gave us a complete profile in terms of that location. So even though you do get early refusal in gravelly soils, which is not uncommon, you know, special procedures like that or special care like that does allow you to still collect data that's valuable. So it's not as simple as just, hey, go out on site and drill, but there are those types of details that are, you know, nuanced among these tests as well.
Mm-hmm. Thank you.
I would add that while it is more difficult than usually, it is not prohibitive in terms of performing CPT, because the issues with refusal were maybe 10-15% of the cases. They were not 50%.
Okay.
So in that sense, it was manageable. So it was not too difficult. It does require more effort, but it is definitely within the reasonable effort margins.
It's doable for professional practice.
Exactly, doable and reasonable for practice, yes.
That's great. It's a good news. I have a question relating to the numerical analysis that Ribu, you show it in the comparison, in the calibration of your model, the comparison between the empirical cyclic resistance curves and the calibration that you did with the stress density model. And you compare the number of cycles was referred to the strength criteria to liquefaction. My question is if you have tried to apply also the stress criteria to look at the pool water pressure instead of the strain, if something is changing or if there is a specific reasons for this comparison.
Yeah, you're referring to the definition of liquefaction triggering, whether it's a strain. Yeah. Look, those types of that was in the consideration in the calibration. We found that calibration to those different criteria were largely quite negligible. The curves sat quite close to each other. There is some systematic bias depending on your criteria, but in terms of propagating those to those results, that they were negligible.
That's great. Thank you.
And if I can go back to the first question around the settlement, which is
absolutely,
great,
absolutely.
That the settlement close to the edges, because of the additional component of lateral spreading, was larger in the observations. I would like to emphasize a couple of important things. The actual settlement includes different mechanisms, and those are volumetric strain. So this is the mechanism that is accounted for in the simplified procedure. Then there is additional settlement due to ejected soils. So some liquefied soils are ejected either on the surface or maybe sideways in this case. So you're going to get settlement because of that. And then there is lateral spreading, which is expansion lateral associated with vertical slumping. So there are three significant mechanisms contributing to settlement in reality. In our simplified analysis, only volumetric settlement is calculated in a simplified manner because it is based on the specific type of test performed in the laboratory where things are quite controlled. When you allow water to gradually and slowly get out of the specimen and you measure volume of water, in reality, the phenomenon is much more turbulent and volatile, and with a lot of things are happening. So in that sense, we only calculate some components of settlement under specific conditions and with a lot of uncertainty. So that is how we should be treating our estimates. Our estimates are quite rough. So we should not be expecting to be very good in predicting settlement estimates, but we should be expecting the simplified analysis is going to give us some indications whether the settlement are going to be relatively small, moderate, or very large. So that is how good our estimates are, not better than that. So I would just suggest that we consider liquefaction induced settlement in our calculations to be of that nature rather than some very accurate predictive tool, because the reality is so complex.
Mm-hmm. Yeah, thank you so much for this suggestion. Let me check
Yeah.
if there are other questions in the chat box. So I encourage the students, if you would like to make questions, we are still here. Okay, I cannot see other questions. So I'm sure that other questions are maybe coming in the next days.
Yep.
So maybe we can contact you again. So I would
Sure,
like to
no
thank
problem.
you again, the speakers, for this outstanding presentation and outstanding discussion. We were very inside the points. I would like to thank all the participants in the teams and also in the live streaming. We have some people that are watching. And I would like to thank Dr. Cironi that make the live streaming possible. And so thank you so much. Have a good evening in New
Thank you, Anna.
Zealand. A
Thank you,
good
everyone,
day
and bye-bye.
to everybody.
Thank
Yes.
you.
Bye-bye.
Thank you very
Ciao.
much.
Ciao.